Right. Good morning, everybody. And for those that were on leave last week, like myself, welcome back to this week's seminar. I acknowledge the traditional owners and their custodianship of the land on which we meet today. On behalf of the Sustainable Minerals Institute, I pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. We recognise their valuable contributions to Australia and global society. Today's presentation is high temperature processing of deep sea polymetallic nodules. It's delivered by Dr. Xiaodong Ma from SMI's JKMRC and the high temperature processing group that has recently joined the JKMRC from chemical engineering. And we do welcome them. And Xiaodong, and we really look forward to your presentation today. As always, if the participants online can submit your questions via the Q&A button at any time during the presentation, and I'll put them to Xiaodong at the end. So Xiaodong, over to you, and thank you very much for your presentation.
Thank you, Neville, for your kind introduction, and also thank Rick to provide this opportunity for me to give a presentation here. So today I would like to talk about the extraction of valuable metals from these deep sea polymetallic nodules. As you may know that deep sea mining that involves a significant novelty that make this utilization of deep sea polymetallic nodules possible. And these nodules are very promising resources for some critical metals. And however, the treatment and extraction of nodules that should rely on some conventional technologies as much as possible. So here, I just focus on the high temperature processing process. By the way, so I'm from a high temperature processing group, and I work with my supervisor, Associate Professor Baojun Zhao. And so at the beginning, I will start with what are the deep sea polymetallic nodules are, and they are also called manganese nodules, which are composed of the manganese and iron oxide concretions. And apart from the major components of manganese and iron, they are also containing some mineral critical metals like nickel, copper, cobalt, molybdenum, vanadium, and a trace amount of rare earth metals. So it's because of these critical metals that the economic interest mainly come from. So and in this video that I got from the National Geography, that these are the nodules looks like. It looks like potatoes, and the size can vary from several millimeters to less than 20 millimeters. It's sitting on the bottom of the sea floor, and then touch with one another. Actually, this is a very high density of the deposits and half buried. So the nodules are normally distributed on the vast abyssal plains of the global ocean, as in this global map. And the blue color represent the deposits of the nodules. And among them, there's one very particular interest that with extensive studies is this area called Clarion-Clipperton zone, which is located in the northeast equatorial of Pacific Ocean. So within this area, that if you see clearly that the different color patterns represent different countries. For example, the China, Japan, Germany, Korea, France, and etc. that they have the license to explore the nodules with their contracted area. So about the formation of nodules, there are several theories to explain the formation of different type of nodules. However, just two of them are popular, which are the diagenetic formation mechanism and hydrogenetic formation mechanism. So both of the two formation mechanism that needs nucleus for the growth of the nodules. So for example, the shark tooth, I think there must be a lot of shark teeth there for the growth of nodules. So in the diagenetic process, that the manganese is remobilized in the sediment column and then precipitate at the sediment surface. And from this process, it will produce the nodule that with high manganese to iron ratio, however with a per nickel, copper, and copper content. And another in the hydrogenetic process, that the iron oxyhydroxide and the manganese oxide are precipitated just from the surrounding sea waters. So this type of nodules usually have a feature of a similar manganese and iron content, and also relatively high grade of nickel, copper, and cobalt. So, so the growth of nodules is extremely slow growing process. The growth rate is just in the order of millimeters per million years. So that means once you harvest the nodules, they are just gone. And if you consider a commercial operation of the mining, that we should consider that whether there will be enough good nodules for the production, like several million tons per year that can last 20 or 25 years. So the exploration and assess the abundance of nodules, that is quite important. And those nodules are containing very complex minerals that mainly are the manganese or iron oxy hydrodioxide that is also doped with some other impurity elements. So in this Clarion-Clipperton zone, it is estimated that approximately 21 billion dry tons of nodules reservoir in there. So it's quite huge. When we comparing the metals in the nodule only in this area with the whole land-based deposit, which is showing the right figure, we can see that for the manganese and the nickel is similar, quite comparable, and copper and nickel are less than the land-based deposit. However, the most interesting thing is that when you look at the cobalt deposit in the nodules is somehow around 3 times of the land-based cobalt. And normally the cobalt is not particular minerals. It's the cobalt exists in the associated minerals. So this cobalt nodules is a very promising resources for the cobalt metals. And for the other elements, I think they can be a very important backup for the land-based resources. So here, when we compare the manganese grade in the nodules and with the standard land-based manganese nodules, As you can see, because it contains some water there, so the nodules, the manganese grade in the nodules is lower than the land-based manganese ores. However, if when we extract the valuable metals and other ions, then the manganese in the nodules will be concentrated. So the manganese grade will be upgraded, and then it will comparable or even higher than the manganese ore. So this will be a very good byproduct and give credits to the value of nodules. And then another thing that we compare with nickel grade between the nodules and the nickel ores. So as we can see, the nickel grade in the nodules is comparable with the nickel laterite. And then we for the sulfide, normally the land-based nickel sulfide is in depression. However, we can find comparable nickel grade in the nodules, but in a very high amount of deposit. So here, currently, before the deep sea mining really come into the commercial practice, so it's only still in the exploration stage to assess the abundance of nodules and also sampling the nodules to determine the metal interest in the nodules. Once or if the economic potential of the area of the nodules is favorable, then it might be possible to move to the mining. However, before the deep sea mining, I would see there is some concern about the environmental impact of the deep sea mining. One is the destruction of a bio ecosystem in the deep sea, because the deep sea mining will destruct the deep sea creatures, and these kind of creatures just live on the nodules. And once their habitat are lost, then they will be extinct. And another concern comes from the pollution that is discharged during this deep sea mining. However, so far, because the deep sea ecosystem just really hard to be fully understood, so this still leave deep sea mining with the environmental impact still uncertainty. So here, as we know that polymetallic nodules are not new. They are first discovered in 1870s, and then the first economic interest came in 1960. However, the commercial activities is ceased in 1980s because of the low metal price. However, the scientific research is continuing. However, why this nodules just regained the widespread interest? Because I think we are now in a very good time to pursue the low carbon future. So and then the battery just very good to use the renewable as the battery is a clean energy. So and the elements like nickel, manganese, copper in the nodules can be used for the increasingly demand for the battery materials. So as you can see, the developing trend of the nickel that contains a high amount of nickel and also high amount of nickel and some amount of cobalt. So we are prepared for the deep sea mining. Then following the mining and the collection of nodules, that is come from the first step is the mineral processing. So mineral processing is normally explored to concentrate and upgrade the ores. However, from this SEM EDS mapping on the elements distribution, the nodule, it shows the major manganese and iron, and also the critical metals of nickel, copper, and titanium, and some other impurity argon elements. So these critical metals are evenly distributed in the nodule matrix. So it is not impossible to separate or enrich the metals of interest from the other nodule components. So these nodules has to be completely destroyed to extract the metal. So the mineral processing that can be skipped, and then it goes to the extractive metallurgy of these nodules. The one is the through the hydrometallurgical route to treat the nodules, and then from the left figure in the curing process, the nodules are ground to fine powder and then reduced by carbon monoxide gas, just in a stirring reactor. This reactor in the presence of ammonia, and then copper, nickel, and cobalt are made soluble in this decanter, and nickel and copper are extracted by the liquid ion exchange and combined with electron wiring to produce pure metals. And the cobalt is removed just by the sulfide precipitation. And from the right figure, in the sulfuric leaching process, again, the same, the nodules are ground to the fine powders, and then it will leached by the sulfuric acid in the autoclave at a low temperature, and then several atom pressure. And then the copper, nickel, and the cobalt are precipitated from the resulting solution, and by this hydrogen sulfide. And the copper sulfide is roasted to give pure copper oxide, while the nickel and cobalt are just kept as sulfides. So here it is noted that the hydrometallurgical route is found to be difficult to recover the manganese from the nodules. So in another extractive metallurgical route is pyrometallurgical route that was zero waste to fully use the nodules. So first, the dried nodules coke of flux are charged in the electric furnace, and to produce manganese-rich slag and iron, nickel, copper, cobalt alloy. And this manganese-rich slag are further directly fed into another electric arc furnace to produce markable high carbon iron manganese alloys, and then leave the heavy metal free slags. Another product is to also produce the manganese rich slag and then the iron nickel copper alloy. This alloy was introduced to the converter for refining to remove most manganese and iron by blowing the oxygen, and then the sulfur was added to produce this nickel copper cobalt matte. So it's a different product for metals. So when we are doing a high temperature processing, so this is the basic principle of smelting reduction of oxides. Is called the Eddingham diagram, which is shown in this figure, and this indicates the thermodynamic solubilities of oxides. So basically, so the oxide located in the lower part is more stable than the oxide in the higher part, and then carbon oxide by oxygen just crosses lines. So when this line is lower than the oxide, it can reduce and strip off the oxygen from the oxide. So then from the nodules, we can do the selective reduction of the metals of interest. So by increasing the reductions, we can control the reduction extent of this oxide, and probably we stop here to fully reduce the copper, nickel, and cobalt, and then partially reduce iron, and then leave the manganese oxide and not reduce in the manganese oxide rich cells. So just this year that we have a collaboration with Nautilus Minerals to do a project to provide some operational parameters for the real plant trials of using nodules to produce some markable metals. And this is air dried nodules that we received from the Nautilus Minerals, which is regionally derived from the CCZ area by the Tonga offshore mining company. It's particular from this area D place. And this table shows the average chemical composition of these nodules. For the manganese, for the metals of interest, that the nodules contain around 40% manganese oxide, and 1.7 nickel oxide, and 1.65 copper oxide, and 0.3 copper oxide. For the molybdenum or vanadium or rare earth metals, the amount is very low, so I didn't show here. This because this amount actually is a very good nodules. So just based on the price of the metals, we just calculate the values of the nodules based on the critical metals and also the major component of manganese. So normally a good nodule is defined as the nickel that contains 1.25 to 1.5 nickels, and then 1 to 1.4% copper, 0.2 to 0.25 copper or cobalt, and 27 to 30% manganese. So these critical metals have very strong values. For the major component manganese is uncertainty because it's unsure that whether these manganese will be accepted as manganese ores, because the land-based manganese ore are still the preferred resource for the manganese alloy production. The other elements just have no values. So when we consider commercial viability, then we calculate the value of nodules to evaluate whether it can make the marginal profit. So here it comes to our research that we selected the high temperature processing process to treat the nodules. It is also our strength that we selected this process in terms of the short processing route and also the massive mass production. And this is a simplified flow sheet of nodules processing that we designed to produce three kind of metal production. One is the Ferroalloys, the ferro-nickel-copper cobalt alloy, and second one is instead of the Ferroalloys, we probably the pure metal is more favorable or accepted by the public. And then with the resident manganese oxide, rich slags can be further reduced to produce either ferromanganese alloy or silico-manganese alloys. So this flow sheet is actually designed to fit or use the current well-established copper smelting process or laterite processing route. So first is the raw nodules are just grind powder, and then add the flux to control the liquidus temperature or the melting point, actually the melting point of the slag, and then adjust the coke to adjust the to selectively reduce the metals. And after drying and production, it goes to a high temperature for the smelting and separation between the slag and the alloys. So also in the mixing stage, we can also mix with addition of sulfide agents to produce the match. So the purpose is we just optimize the slag and then the alloy grade, just try to achieve a low temperature operation and then save the energy in this carbon thermal reduction. So at the beginning, then before we conduct the experiment, and we use a commercial software, FeXage, to modeling the liquidus temperature. So the liquidus temperature, actually the melting point, you can understand as a melting point of the slag that is operate at high temperature. So from this average chemical composition of the nodules, we just assume we pick up the major components and then assume the all the critical metals are fully recovered, and then just ignore the minor elements that we pick up as the bottom table, the components, and then calculate this liquidus temperature of the slag. It is around 1550 degrees, so which is very quite high. So based on this composition, then we're going to further optimize this composition and then to achieve a low liquidus temperature. So here is the modeling result. So the iron oxide, calcium oxide, and aluminum oxide, so which is the major component in the nodules, it also can be used as a flux candidate to be added in the slag. So we first examine these three components to see how is the effect of this oxide effect on the liquidus temperature at different manganese oxide to silica ratio. So from these three figures, overall you can see that the iron oxide, calcium oxide, or aluminum oxide, the slag they actually have very little effect on the liquidus temperature. So that means the change of this oxide will not have a significant influence on the liquidus temperature. However, by changing the manganese to silica ratio, if we decrease the manganese to silica ratio, then we will significantly reduce the liquidus temperature slag. So that means only the silica can be used as a flux to further reduce the liquidus temperature of the slag. Then we just use the silica as a slag, as a flux, and then to calculate with the addition of more silica to the nodules, how is the liquidus temperature change. As we can see, this is the liquidus line. So about this line, that the slag can be operated in the full molten state. So with the addition of silica, then the liquidus temperature dramatically decrease. However, we cannot add the silica as much as possible because we also need to consider the viscosity of slag, because silica actually increases the viscosity of slag. And then in the first stage to produce Ferroalloys, we add different amount of silica as flux just to optimize the ratio of the flux, and also we add different amount of carbon as a reductant to produce different composition of the ferroalloys. So here is our high temperature experiment, and this is a schematic of high temperature furnace we normally use. At high temperature, we normally refer to over 1000 degrees, and this high temperature furnace even can reach up to 1650 degrees. So it just made to fulfill our experimental purpose. So in the production of the nodules at 1000 degrees in the argon gas, just remove to dry the nodule, and also pre-reduce the copper, nickel, cobalt, and partially reduce the iron, just to achieve a high recovery rate of these metals. And then in this smelting reduction, also to complete the reduction and then separate the alloys and the slag, and then leave the manganese-rich slag for the further production, smelting reduction. So, and at an even higher temperature, like 1550 degrees, manganese silicon alloys are produced. And this alloys is normally used for the steel making, and then the slag can be used ceramic glass. So this is ideally a zero waste of fully using the nodule components. So this is a result that we extract the critical metals to produce ferro alloys that at 1350 degrees, that will vary the carbon from 2% to 8%. So basically, the slag and we got alloy and then separate with slag. The slag at high temperature is the molten state. However, when it quenches the water, it cools very quickly and then has no time to crystallize. Then it become a glass. So it's very brittle glass here and the slag. So this is an indicator that we can optimize the slag into at a low temperature and also achieve a full molten state. And then by this is changing the silica ratio from 10% to 5%. Also, the glass, the slag is glass. So here is a result of optimize the carbon ratio. So by increasing the carbon addition, that first we reduce the alloys and then leave the slag as a glass phase. So this is alloy composition. Then we can get the iron, copper, nickel, copper alloys, and in this from this slag we can indicate almost the copper, nickel, and the copper oxide are fully reduced. So here is the effect that the copper, nickel, cobalt concentration in the reduced alloy that change along with the carbon addition. So in this area one, when the carbon is added insufficiently, so no alloy is reduced, and if the excess carbon is added, then the manganese will be reduced. This is not what we expect. So probably the optimized area is in this area, in the middle. Then we can adjust the reductant to get the desired alloy grade. So this is the result that we optimize the flux by increasing the flux. That we still have the solid in the slag. This is not favorable because it will have a very high viscosity of slag, and it will be very difficult to tap the slag and separate from alloy. By increasing this silica, that we can get the full molten state slag, and also the alloys produce that copper oxide, nickel oxide, and copper oxide are fully reduced from the slag. So here is we compare the our experimental temperature and then calculate the liquid temperature of the slag. So there is still some room to further reduce the experimental temperature. And then with the addition of the flux, we just examine how is silica that influence the viscosity of slag. So then we calculate the viscosity. It's just below the 0.22 Pascal second. Then this is in the safe slag viscosity for the operation. And then we use the MATSIM software to modeling the mass balance and energy distribution in this nodule process treatment. So this is a simplified process flow sheet that is just referring to the laterite smelting process, which is mainly contain the rotary kiln furnace for the nodule drying and casting, and also the production, and then the further feed to the electric arc furnace for the smelting reduction. So here I use natural gas for the fuel source and heating. And this is MATSIM modeling result of the flow sheet. We just make the model is just we make a design to simulate 100,000 tons per year production process to treat the nodules for the nodules capacity production, and then in the rotary kiln, so we simulate the temperature is around less than 1200. Should be around 1000 degrees, and then without the flux addition, that in the electric furnace is around 1550 degrees. That the ferroalloys was reduced around 70% iron, 3% cobalt, and around 15% nickel and copper. And in the second stage is we extract the instead of making ferroalloys, and we add some sulfur agent to produce iron, nickel, copper, cobalt matte. So this matte should be integrated with hydrometallurgical process, and then finally to produce pure metals. This is maybe more favorable for the market product. However, we just did a preliminary experiment to produce this matte that we doped the sulfur as calcium sulfate, and at the 1350 degrees with 4% carbon as a reduction. And this is got from a previous study, and then 10%. We just try 10% for calcium sulfate addition, and also 5% of calcium addition. And then we get the full molten state slag at low temperature, and then which has a very good separation of alloy from slag. And from this, the table shows the composition of slag and alloys. So sulfur is doped, is not as high as what we expect. Probably in the future, we're going to add other sulfate agents like the pure sulfur or iron sulfate to make the high sulfur matte. That may be favorable for the further hydrometallurgical process. So with the resultant manganese-rich alloy, then we extract the silico-manganese alloy, and from this slag to make the manganese silicon alloy. This is widely accepted, can be widely accepted as the master alloys for the steel making use. So here, again, we just also carry out two experiments at 1500 degrees with 10% and 50% carbon addition at the reduction. This is done in a graphite crucible. So graphite can also further reduce the manganese slag, manganese oxide slag. So this is the table also shows the slag composition and also the alloy composition. So here's a manganese-rich silicon and iron alloys. However, when we see the composition of manganese in the slag, and also contain a high amount of manganese oxide. This is probably because the kinetics that we in our lab experiment is probably slow, just in 1 hour reduction. However, in the industrial electric arc furnace provide a good kinetic and can achieve a higher reduction of manganese oxide reduction. So finally, and last is my summary. Just give a short summary here that enormous tonnage of nodules on the seabed can meet the increasingly demand of critical metals in our low carbon future. And these opportunities are very close to open a new industry with the development of high technique, developing mining, and should be have a better understanding the environmental impact and risk, and high efficiency and low cost for the attractive metallurgy. And then we just carry out our high temperature processing polymetallic nodules to recover the valuable metals, just towards zero waste and energy saving route. So we just try to get some Ferro Alloys, matte, and then silico-manganese alloys. These product options for the market acceptance. I think further use of nodules really depend on the cost or the value of metals in the market. And so I think that's all my presentation. And thank you for your attention. Thank you.
Right. Xiaodong, thank you very much for your presentation today. It's really interesting to see the high temperature work and see the processing of those nodules. For those that are online, we have time for a couple of questions. So if you would like to go into the Q&A button at the bottom of your screen and post your questions there, I will then put those questions to Xiaodong from you.
I've got one.
You've got one? Okay, if you want to do that while we wait for people just to type in a question.
I mean, it's really interesting to see the business end of the actual processing, because I think quite a few of us are involved in, to some extent or another, in thinking about deep sea mining and looking at a sort of high level at the high temperature processing without, certainly in my case anyway, having a detailed understanding of it. But one of the more compelling things around deep sea mining, I guess, is the fact that the climatic footprint of deep sea mining has the potential to be so low compared to the terrestrial equivalent, and you know, there've been some publications on that quite recently. But my question is the you know, did your work really optimize the potential to minimize the kind of energy usage for smelting? Do you think that we can make more you know, more progress in that area, or is you know, what you presented the best we can do?
Yes, yeah. So I think for the nodules, we try to reduce the liquid temperature slag. It's actually so when we use the nodules, we should consider the existing technologies to use the nodules. So we consider currently we consider two processes. One is the the copper smelting process. So so produce a matte in a copper smelting furnace. Normally, the copper smelting furnace, the operation temperature is around 1100. So we try to reduce the slag liquid, the melting point slag, to 1100. If we can achieve that, then that means we can we can treat the nodules in a copper smelting furnace. That we can save the capital and also the operation cost. So we don't need to build any new furnace. So in the copper smelting furnace, then we can make a matte, and then once we get the matte, it can be further proceed as normal as like copper matte. So this is one production route, and another production route is use the laterite. You know, laterite is a nickel oxide, all right. So nickel, we can use the existing rotary kiln and also electric arc furnace to treat the nodules to produce ferro alloys. And then in the electric arc furnace, normally the temperature is around 1500 or 1600. It's quite high. So we try to optimize the slag composition to reduce the temperature. Maybe around now we can achieve like 350 degrees or just around 300. So we can dramatically reduce the temperature and then to save the energy. So this is two process, and we can use to treat the nodules.
Thanks.
So we don't have to put any capital or another additional operational cost, and then we can reduce the temperature. Then probably just make the nodules utilization close to the market. Yeah.
Thanks.
Yeah.
All right. Got a question here, and I'm going to do my best to put this to you. Is there a significant difference with the work that was done by the German group, and I think it's from Aachen?
Yeah.
And what is the innovative angle? So I'm assuming you know the work that's been done in Aachen, and what would the difference be between the work you're doing and there?
Yeah, I actually read that the paper they published. I would say it's similar, but in terms of the optimization slack and also the reductant, I think we did a more systematic research in our group, and we just try to lower the achieve a lower temperature, liquid temperature slack. Yeah.
All right, and then the other question you have answered part of it, but it was more around, can you comment on the total commercial viability of processing these polymetallic nodules? So if you were to look at it as a total commercial entity, have you any idea of whether it is commercially viable?
Yeah, I think it's commercially viable apart from the environmental impact consideration, because I don't know how is the cost of the deep sea mining and then the transportation to the onshore. But in terms of just from the high temperature processing, I think it's commercial viable, because we already have the well-established technologies, like I mentioned before, the copper smelting furnace or the laterite smelting furnace. Then all can be used to treat nodules. So we don't need any new or additional capital or operation cost. So once so if the cost of deep sea mining is economic, then once the nodule is transported to the onshore, then I think it's commercial viable.
All right. Well, Xiaodong, thank you very, very much for your presentation today. It was fantastic to see the work that you're doing, and very interested to follow it and see how you progress. We don't have any more time for questions, so I'm just going to move on to next week's presentation. And next week, we want to have one of our newest adjunct professors joining us, and it's Dr. Kobus de Jager, and he'll be giving a presentation on safety, a business imperative. And I look forward to seeing you all again next week for the seminar, and I'd like to thank everybody for your participation. And Xiaodong, thanks again for your call.
Thank you. Now we are on a break.
Great.
Thanks very much.
Thank you.